Hey, welcome back to the channel of Roller Coaster with Math. In today's video, we are exploring a fundamental concept in linear algebra, what it means to have a linear transformation. T, which is the function from Rn to Rm. We will break it down step by step using simple examples and visuals to make it all click. Let's get started. When we say T from Rn to Rm, we are describing a linear transformation that maps vectors from an n-dimensional space to an m-dimensional space. This transformation is represented by a matrix A and it acts like a machine. So for example, this is the matrix A and we input a vector from Rn and the transformation through matrix multiplication gives you a vector in Rm. The linear transformation T of x is written as T of x equals to A times x where A is the transformation matrix. Which is m times n, and x is a vector in Rn, the input space. And T of x is a vector in Rm, the output space. Let's try an example. Suppose we have a matrix A 1, 2, 0, 1, 3, and 4, and x vector with x1, x2, when we compute T of x equals to A times x, we get T of x equals to 1, 2, 0, 1, 3, 4 times x1, x2. Then we calculate them. x1 plus 2x2 and x2, 3x1 plus 4x2 So for any input x in R2, we get an output t of x in R3. Input x in R2, we get output t of x in R3. So this means that t transforms 2D vector into 3D vectors. There are some key questions to analyze t. Now let's understand t by answering two key questions. 1. Is t 1 to 1? 2. Is t onto? First, let's check if t is 1 to 1. To check if t is 1 to 1, we look at the kernel of t, which is the set of all vectors x in Rn that are mapped to a zero vector in Rm. This reads as the kernel of t is the set of all vectors x in Rn, and t of x equals to 0. If the only vector in the kernel is the 0 vector, then t is 1 to 1. Now b onto. To check if t is onto, we look at the image of t. Which is the set of all possible outputs of t of x. This is also called the range of the transformation. The image of t, which is the set of all possible outputs of t of x. If the image spans all of Rm, then T is onto. Here's a powerful result in linear algebra, the rank-analytic theorem. It connects the dimensions of the kernel and the image. The formula is given as rank of A is the dimension of the image. And the nullity of A is the dimension of the kernel of T. This equation tells us how much of Rn is mapped into Rm and how much is lost along the way. We can see some examples. Of T mapped from Rn to Rm. T is mapped from R2 to R3. Suppose A equals to 1, 2, 0, 1, 3, 4. This transformation maps a vector from R2 to R3. The image is the plane in R3, and the kernel would be a subset of R2. Now consider A equals to 1, 0, 2 and 0, 1, -1. Here, T maps 3D vectors to 2D vectors. The image of T is the plane in R2. Kernel of T is the line in R3. And next, we have T mapped from R2, T mapped from Rn to Rn, when n equals to m, the transformation could be invertible. Meaning that T of x is both 1-to-1 and onto. And that's how linear transformation like T is mapped from R2 to Rm works. To summarize, they map vectors from one space to another. Using matrix multiplication, and the kernel tells us about the one-to-one behavior. The image tells us about onto behavior. And the rank-nullity theorem ties it all together. If you found this explanation helpful, be sure to like, subscribe, and let me know in the comments what math concepts you'd like me to tackle next. Thanks for watching, and see you in the next video.